Hello and welcome to this tutorial. Today, we are diving into the world of automata theory to understand deterministic finite automata or DFA for short and how we can visualize its working using Python. So sit back and get ready to learn. Let's start by understanding what a DFA is. A DFA is a computational module used in automata theory to recognize patterns or validate strings based on set of rules. Think of it like a maze where the start state is the entrance and transitions are the paths you take based on inputs, and the final state is the exit. If you end up in the exit state after consuming all the input, the string is accepted. Otherwise, it's rejected. A DFA is deterministic, meaning that for any given state and input, there is exactly one defined transition to the next state. This makes it predictable and easy to implement in computational systems. Now that we understand what a DFA is, let's take a look at the Python code we'll be using to implement and visualize it. The program not only validates the string based on a DFA, but also create an animated GIF showing how the string is processed, step by step. Here is how the code works. First, the valid underscore with underscore steps function checks if an input string is accepted by the DFA. It takes the transition table input string start state and final state as input. As it proceeds each character, it keeps a track of current state and stores the steps for later visualization. Next, we have plot underscore to underscore GIF function. This function uses the network X library to create a graph representation of DFA and PIL library to save frames of each steps as images. These frames are then compiled into a GIF to visually demonstrate how the string transitions through the DFA. The main function tries to define the DFA by entering states, alphabets, transitions, the start state, and the final state. After that, you can input the strings to validate them against the DFA, and the program will generate a GIF showing the process. Let's see the code in action. The program checks the string and generates this GIF to show the transitions through the DFA. As you can see, the DFA processes each character step by step and finally ends in the accepting stage Q2. This means the string is valid according to our DFA. That's all for today's tutorial. We have learned what a DFA is, explored how to implement it, Python, and created a cool animation to visualize its working. If you found this tutorial helpful, don't forget to like, share, subscribe to the channel. Drop a comment if you have any questions or suggestions for the future. Thank you for watching. Shubharatri.
Delving into Parse Trees. Welcome to our exploration of Parse Trees, a fundamental concept in computer science, particularly in the realm of programming languages and compilers. Slide 1. Introduction to Parse Trees. The presentation, Delving into Parse Trees, introduces parse trees as hierarchical structures essential in computer science, particularly in programming languages and compilers. Parse trees visually represent the syntax of sentences or expressions, with each node corresponding to a grammatical rule or symbol. Slide 2. Importance of parse trees. Parse trees are crucial for understanding syntax, enabling the analysis of how sentences conform to grammatical rules. They play a vital role in compiler design by converting source code into machine-readable instructions and are equally important in natural language processing (NLP) for interpreting the meaning of sentences. Slide 3. Structure of parse trees. Parse trees consist of three components: the root node, representing the entire sentence or expression, internal nodes, corresponding to grammatical rules or non-terminal symbols, and leaf nodes, which are terminal symbols like words or punctuation. Slide 4. Constructing parse trees. Parse trees are built through a three-step process: lexical analysis, where the input is scanned for tokens; syntactic analysis, which parses tokens based on grammar rules; and tree construction, where the hierarchical structure is formed to represent the syntactic relationships. Slide 5. Ambiguity in parse trees. An ambiguous parse tree allows multiple interpretations, causing semantic confusion and challenges in compiler design. In contrast, a non-ambiguous parse tree has a single interpretation, ensuring clarity and efficient compilation. Slide 6. Checking for ambiguity. Ambiguity in parse trees can be checked through manual inspection for multiple possible interpretations, formal analysis using formal language theory, or compiler tools that automatically detect ambiguities. Slide 7. Applications and conclusion. Parse trees are widely applied in programming languages, compiler design, and NLP. They facilitate syntax analysis, semantic understanding, and efficient code generation, making them indispensable in both computing and linguistic fields.
Hello guys, welcome to our TOC project. Our project title or the name of our project is CFG Ambiguity Checker, which checks whether the given string is ambiguous or not. So introduction to the formal languages. So the type of grammars we have is the context-free grammar, the context-sensitive grammars. So the context-free grammars have four tuples, that is V, T, PS. V is the non-terminal, T is the terminal, P is the production rule, and S is the start symbol. And to check whether the context-free grammar is whether ambiguous or not, there are some certain conditions. So the first condition is the parse tree, where the given string should have more than one parse tree and more than one left derivation tree and more than one right derivation tree. If any one of these conditions are true, then it is an ambiguous. This is the Python code to check whether the given string is ambiguous or not, and we have used functions like matplotlib and other functions as well. So we can see that the first example and the first string is AB, and we have given a recursive call, and the output is that the string is unambiguous, and the program have generated a single tree, and this is the single tree. So if there is a single tree, then the string is unambiguous as per the condition. So this is the second example, and in this example the output is that the string is ambiguous and it has generated the three trees. So the three trees according to the code has been displayed here in the output. So this is the first tree, the second tree, and the third tree. So as per the condition, if there are one or more trees, then the string is ambiguous. Thank you.
Welcome everyone. So our project focuses on context-free grammar transformations, a fundamental concept in theory of computation that plays a critical role in language processing and compiler design. So our problem statement is CFGs can become complex with redundant rules like null productions, unit productions, or useless symbols. These complicate parsing and increase computational overhead. So our project aimed to simplify CFGs while preserving their language equivalence. For this, we have used the PyCFG library available in Python for implementing grammar transformations. It provided a robust framework for parsing and modifying grammars. CFGs can become complex with redundant rules like null productions, unit productions, or useless symbols. These complicate parsing and increase computational overhead. Our project aimed to simplify CFGs while preserving their language equivalence. Chomsky normal form, the grammar was transformed into CNF, where rules are standardized for efficient parsing. This form is crucial for algorithms like CYK parsing used in compilers. Removing null productions. Null productions which generate an empty string were eliminated by rewriting rules while preserving equivalence. Here you can see the examples. Removing unit productions. Unit productions like A implies B were replaced with the rules of B to simplify the grammar. Here you can see the examples. Eliminating useless symbols. Symbols that do not contribute to string generation or are unreachable were removed. Here you can see the examples. Here in this example, the C is not defined in the main string, so C is useless as it cannot be reached from S or generated. In this code, we have used the Python library PyCFG and we have used the tkinter, where tkinter is a Python library that allows users to create graphical user interfaces. And now next we'll proceed on with how to run the code and see the solutions. Now we'll proceed on with giving the inputs and getting the output for the following. Firstly, the context-free grammar, shortly called as CFG. It is a formal grammar used to define the syntax of programming languages and structured data. And the components of CFG are non-terminals, terminal, start symbol, and production rules. Here we are giving the example, you can see, and at the down we have to specify what are the variables, start variables, terminals, and null characters. And when we give as a evaluate, it will tell us whether it is a valid string or not. Now it is a valid, so it showed as a valid. Now we'll check for another string where it is whether so it is invalid string. Now next we'll move on to Chomsky normal form, shortly called as CNF. It is a standardized form of CFG where every production rule is one of the following, where one non-terminal tends to two non-terminals on the right side and one non-terminal tends to a single terminal on the right hand side. So now we can see the example and now we can check for it. So here we can see it is being converted into the Chomsky normal form. Next is removing the null productions. Null production, a rule like A tends to epsilon, where epsilon refers to an empty string. The problem is that it can lead to ambiguous derivations. The solution is that identify nullable variables, replace rules that depend on nullable variables by including alternatives without them. Here you can see the example. S tends to A, S, A, where A tends to null. Now it will be removed. Yes, now we can see that it is being removed. Now next we'll check for removing the unit rules. Unit production rule says that a rule where a non-terminal maps directly to another. The problem is adds unnecessary steps during parsing, which leads to inefficiency. The solution is replace unit productions with the rules of the non-terminal they point to. Example can be seen on the screen and it has been removed the unnecessary steps. Next, we'll move on to removing the useless symbols. We have two types of useless symbols. One is non-generating symbols that cannot derive any terminal strings. The second is unreachable symbols, never appear in derivation starting from yes. The solution is identify and remove these symbols to optimize the grammar. Here we can see the example on the screen and we are giving the variables. Variables is the non-terminals that we have to specify, and then the terminals, and then evaluate, and then now we can see the useless symbols has been removed, and C is useless as it cannot be reached from yes or generate string. And here is output. Thank you.
So our group's topic is conversion of CFG to PDA. So CFG is a formal set of rules used to define the structure of strings in a language. It is primarily used in programming languages, natural language processing, and automata theory. So there are four components in CFG, namely VTPS, where V stands for non-terminals, T stands for terminals, P stands for production rules, and S stands for start symbol. And PDA, which is push-down automata, it is a seven-tuple which has Q alphabets, to, row, Q0, Z0, and final state. So to convert from CFG to PDA, the CFG to PDA converter class is initiated with variables, terminal, and start symbol along with production rules. To convert it to PDA, the we use the method convert to PDA, in which we add a transition to start the PDA by pushing the start symbol onto the stack, and then for each production in the grammar, if the rule involves replacing a variable with another set of symbols, it is added as a transition. And then for terminal consumption, we add transitions to process terminals. The PDA removes the terminal from the stack when it matches the input. Then the accept state adds a final transition to move the accept state when the stack is empty, signaling that the string is valid. Then we'll display the PDA, which involves display PDA method, which prints all the transitions created in a readable format. Then we have our output, which which has the start transition. The PDA begins by pushing the start symbol onto the stack. Then if a variable in the stack needs to be replaced using the grammar rules, transitions are added. These transitions ensure that the stack matches the structure defined by the grammar. Then terminal processing. If a terminal is found in the stack and matches the input, transitions are added to consume it. This reduces the stack and ensures that the input is processed. Then the accept state. When the stack is empty, the PDA transitions to the accept state. Finally, the printed transitions show all the steps the PDA follows to parse the input and verify if it belongs to the language defined by the CFG. Thank you.
Welcome to this presentation on DFA minimization, prepared by Abhishek Hujratti, Brijesh M, Dhanush GS, Harkishan CS. and Mohan Kumar G. Deterministic finite automata, or DFA, is a formal system represented as a 5-tuple Q, sigma, delta, Q0 and F. Here, Q is the finite set of states, sigma is the input alphabet, delta represents the transition function, Q0 is the start state, and F is the set of final states. DFAs are commonly represented as state diagrams to visually demonstrate transitions between states based on inputs. DFA minimization helps reduce the number of states in a DFA by eliminating redundancies while preserving its functionality. For example, in a DFA accepting repeated inputs of A or B, certain states may be unnecessary. Two DFAs are equivalent if they accept the same language. DFA minimization ensures that the equivalent DFA uses the minimal number of states required to perform the same function. The process involves combining states that behave equivalently, making the DFA more efficient. The task of DFA minimization can also be applied to NFAs, as converting an NFA to a DFA precedes its minimization. Several algorithms exist to achieve this, including one that uses a lower triangular table to identify distinct states iteratively. In this method, states are marked distinct if one is final and the other is not. Using inductive definitions, we identify equivalent states and merge them. This process continues iteratively until no changes occur, resulting in a minimized DFA. For example, in a simple DFA with states S0, S1, and S2, the algorithm identifies S1 and S2 as equivalent. These states are then merged to produce a minimized DFA. More complex DFAs may require multiple iterations of this process, but the end goal remains the same, achieving an efficient representation with the least number of states. DFA minimization has practical applications in areas such as regular expression matching and compiler optimization, where it helps eliminate redundancies. The described algorithm has a complexity of O, while Hopcroft's algorithm improves efficiency to O. In conclusion, DFA minimization is a fundamental and practical technique that simplifies automata while maintaining their essential properties.
Hi there. So we will be seeing how push-down automata works with the help of our model. So push-down automata is a finite automata with extra memory called stack, which helps us recognize context-free languages. So the working structure for push-down automata is as shown in the figure. We'll be providing a input tape to our machine. The input will be passed on to the control unit, which uses the help of a stack to decide whether to accept or reject our input tape based on a problem statement. So pushdown automata is a machine that can be defined using all the 7 symbols mentioned here. So Q is the set of states which is a finite set of states, like in our example it's Q1, Q2, Q3 and Q4. So sigma is the set of input symbols for which we'll be determining whether to accept or reject our input stream. So in our context, in our current scenario, we have symbols as 0 and 1. So after this we got is the set of which can be pushed and popped from the stack delta. So this is nothing but again our zeros and ones, because only 0 hash and 1 can be pushed onto the stack. So these will form the set of push down symbols, and Q0 is the initial state, so in our context it's to be 1. Z is the initial push down symbol. Okay, so F is the final set of final states. In our example there is only one final state, that is Q4. And transitions, like for example Q1 comma 0 gives us 0, Q3 comma 1 gives us lambda, and so on. So in our current example we will be learning how PDA works for the example 0 power 1, 1 power n when n is greater than or equal to 0. To accept strings that have equal numbers of zeros followed by equal number of ones. So in our example, let us consider double zero and double one, and let us start a model and visualize how the process in pushdown automata works and whether the string has to be accepted or not. So starting with our first step, so we are gonna be in our Q1 state. So next step, as soon as we encounter a 0, we'll be moving on to the Q2, which will be pushed onto the stack, and again a 0, which will be pushed another 0 on the stack. For our current example, as soon as we encounter things other than 0, that is 1, we'll be eliminating, that is popping out the 0 which was initially pushed onto the stack. So let us go through. So we are done with two zeros, two input variables done. So now the next variable is gonna be 1. So using that 1, we are gonna pop the first 0 which was on the top of the stack, and again another 1 which will give us 0, Q3, and at the last step, as there are no variables left, it moves on to Q4, that is the final state, and we can see that our string is accepted, which because it has reached to the correct final state. Machine has reached to the correct final state. So we are gonna look in another example by taking double zero triple one. So let us start this. So initially we are gonna stay on Q1. As soon as we encounter 0, which will be pushed onto the stack, and another 0 which will be pushed onto the stack again. Now there are two zeros and three ones, so there is one extra one here, so which is not possible for a string to be accepted. So in this case our machine won't reach to a final state, which indicates that this is not a valid string and the machine has rejected the input string. So as soon as we encounter the first one, we are gonna pop first 0 out, again pop the second 0 out, and next we are left with one more 1 which cannot be, as there is no transition defined by one that moves on to the final state. We are going to stay on the same Q3. So next step is rejected, incorrect final state. So if at all we pass equal number of zeros followed by equal number of ones is when our string gets accepted, or else it gets rejected. Thank you.
Hello everyone. Our topic is on pumping lemma for regular expression. Our code is based on C language. The pumping lemma for regular expression is a tool used to provide the certain languages are not regular. Our code aims to apply the pumping lemma. For the language to be regular, it must follow the three rules, where v, u and v less than or equals to p, where p is the pumping length, and v must be greater than or equals to 1, for all I greater than or equals to 0, where u v to the power I and z must belongs to L. Now provide the value of n so that we can perform the pumping length. Construct the word and divide the word into three parts u, v and z. Execute the pumping lemma. Checks if u, v to the power I and z belongs to L. Iterates to the word and sums the value of 0 and 1. Checks if the language is regular or not. Now if we execute the code, we can see the output where in the beginning it will tells the rule which must be satisfied, and then it will ask to provide the value for n, which is pumping length. Now let's provide the n value as 3. Here we can see the output. In the beginning it will generate the strings of zeros and ones, and it will divide into three substrings u, v and z. Then it will iterate through 0, 1 and 2 and checks whether the language is regular or not.
Welcome to our demonstration on input validation and structured data handling. Today we'll explore usernames, dates, and email addresses while ensuring accurate processing. Now, username. First, let's review some usernames. The valid ones are valid underscore user underscore 12 and admin. However, invalid.username does not meet the required criteria. Dates. Next, let's examine the dates recognized as valid are January 15, 2023, 2023.01.15, and February 29, 2024, a leap year date. Fortunately, there are no valid examples here. Email addresses. Now, for email addresses validation, correct formats are john.doe@example.com and user@example.com. However, invalid.email@domain.com and excessively long emails such as long underscore user underscore plus excessive character fail the check. Now, this includes a validation overview. Remember, ensuring clean and accurate input vital for effective data handling. Thank you for your attention.
Push-down automata. In the theory of computation, a push-down automata is an abstract machine used to model computations for context-free languages. It extends the capabilities of a finite automata by incorporating a stack which provides additional memory. Key features of a PDA. Input tape reads symbols from an input string one at a time. States has a finite set of states to represent computation stages. Stack. A stack is a last in first out storage, allows the PDA to remember information such as matching parentheses or nested structures. Transition function depends on the current state, the input symbol, and the top symbol of the stack. Can move to a new state, push symbols onto the stack, and pop symbols off the stack. PDA components. A PDA is formally defined as a seven tuple that includes finite set of states, input alphabet, stack alphabet, transition function, initial state, initial stack symbol, and set of accepting states. How it works. Starts in an initial state Q0 with an empty stack or a predefined stack symbol Z0. Reads an input symbol, checks the current state and top symbol of the stack, performs one of the following: push a symbol onto the stack, pop a symbol from the stack, move to another state. The process continues until the input string is processed. Acceptance criteria. A PDA accepts a string if it reaches an accepting state or the stack is empty at the end of the input. Significance. PDAs recognize context free languages like balanced parentheses or palindromes used in parsing programming language and grammar checking. Context free grammar. In the theory of computation, a CFG is a formal grammar used to define context free languages. It is a key concept in formal language theory and is widely used in parsing, compiler design, and natural language processing. Definition of CFG. A context-free grammar is a for tuple that includes a finite set of non-terminal symbols, a finite set of terminal symbols, a finite set of production rules, and a distinguished start symbol. How CFG works. Start with the start symbol, apply production rules recursively to replace non-terminal symbols with strings of terminals and or other non-terminals. The process ends with only terminal symbols are left. Derivations. Leftmost derivation. Replace the leftmost non-terminal at each step. Rightmost derivation. Replace the rightmost non-terminal at each step. Parse tree. A parse tree visually represents the structure of derivations. Root, the start symbol, internal nodes, non-terminals, leaves, terminal symbols. Significance of CFG. Formal definition of languages used to describe programming languages such as arithmetic expressions and syntax. Parsing, essential for building parsers in compilers. Decidability. Efficient algorithms exist for checking membership in CFLs. Example, using a push-down automata. PDA to CFG. To convert a push-down automata into a context-free grammar, We construct a grammar that generates the same language as the PDA recognizes. This process ensures that every string accepted by the PDA can be derived using the CFG. Thank you.
Hello everyone, myself Karan. My team Kushal, Davis, Abhi and Manish are going to present a topic on NFA to DFA. So this is the presentation. So this is the working code to convert NFA to DFA. As you can see, we have implemented it using Python and using some libraries, using Pandas, graphic viz to view the graph at the end. And this is the input. So the number of states is 3 and the number of transitions is 2. State name, as we continue to give the input, finally we get this output. This is the graph for the input that we give. Thank you.
Hello everyone. Today I'm here to present our theory of computation project NFA to DFA converter. So here we have few options where we can like create the NFA visual representation. First we add the state. So first state we have is Q naught, and then again we add state. The next state is Q1 and the third state is Q2. Now we add the transitions using this. So first we have the transition Q naught and the symbol is A to Q naught. Then again we again add transition Q naught B to Q naught. Add transition Q naught A Q1. Add transition Q1 B Q2. So this is our NFA, non-deterministic finite automata. Here we create an accept state, that is Q2, and set the start state, which is Q naught. So this is our final visual representation of NFA. And this is, here we can see, is the transition and all the details about this. Now here we can just zoom in, zoom out, and then we just convert NFA to DFA. As you can see, this is the deterministic finite automata visual representation, and this is the details regarding that. And we have the table here as well for the deterministic DFA transition table. We have it here, and these are the instructions that one can follow to complete the procedure. So this is the visual, the final DFA. Thank you so much.
CFG to CNF conversion using Python. Presented by Ramu BT, Sai Kumar SL, and Mallikarjun Hirur. The image discusses context-free grammars in Chomsky normal form. What is a context-free grammar, CFG? 1. It's a formal grammar used to generate languages. 2. Rules are in the form, a right-pointing arrow beta, where A is a non-terminal symbol, and beta is a string of terminals and/or non-terminals. And 3. Example. S right-pointing arrow ABC. A right-pointing arrow A, B. B right-pointing arrow B, C. C right-pointing arrow C. What is Chomsky normal form, CNF? It's a restricted form of CFG where all rules are in one of the following forms. A right-pointing arrow BC, where A, B, and C are non-terminals. A right-pointing arrow is a non-terminal and A. Importance. CNF simplifies parsing algorithms, making it easier to analyze and process languages. It's crucial for proving certain theoretical results in formal language theory. The image discusses context-free grammars in Chomsky normal. Project approach. Steps involved. 1. Input. Get the CFG from the user. 2. Eliminate epsilon productions. Remove rules of the form right pointing arrow epsilon. 3. Eliminate unit productions. Remove rules of the form right pointing arrow B. 4. Eliminate terminals in longer rules. Introduce new non-terminals for terminals in rules with more than one symbol. 5. Binarize rules. Convert rules with more than two symbols into binary rules. And 6. Output. Display the resulting CNF. This image presents a set of instructions or guidelines for showcasing the Python implementation of a context-free grammar, CFG, to Chomsky normal form, CNF, converter. Here's a breakdown. Python implementation, code snippet. The instructions request a key code snippet, such as the eliminate underscore epsilon function, which likely plays a crucial role in the conversion process. They also ask for a brief explanation of the logic behind the code. User input and output. This section emphasizes the importance of demonstrating how a user would input the CFG into the program. It also highlights the need to showcase the expected output, which is the CFG in CNF. Demonstration, optional. This section suggests optionally including a short video or live demonstration of the program in action. This slide titled Conclusion outlines 2 key points for wrapping up a project presentation. Summarize the project and its significance. This is where you provide a concise overview of the project's goals, methodology, findings, and impact. Discuss potential extensions or improvements. This section allows you to highlight future directions for the project, such as adding error handling mechanisms, developing a graphical user interface, exploring additional features or functionalities. Thank you.